Welcome to The Explainer. Today, we're unpacking the evolution of the oldest and, let's be real, arguably the most foundational engineering branch in human history, mechanical engineering. We're going to look at exactly where this incredible field started, the absolute gauntlet required to become a professional today, and the powerful software ecosystems that are completely redefining how we build the world around us.
It's a fascinating question, right? I mean, we're looking at a really profound contrast here. On one hand, you've got the ancient, highly tactile, physical world of early engineering. Think of massive wooden gears, the literal sweat of human and animal labor, and the raw physics of lifting heavy stones. On the other hand, you have today's cutting-edge digital ecosystems, where components destined for the actual vacuum of space are entirely conceptualized, built, and stress-tested inside a computer, way before a single piece of metal is ever cut. All right, Section 1, Origins of Mechanical Engineering. Okay, let's dive right into this. To really appreciate the complex software running on a multi-core processor today, we have to look back at the foundational physics our ancestors were mastering thousands of years ago. The roots of mechanical engineering run astonishingly deep. We start way back in prehistory with simple machines, stuff like the wedge and the inclined plane. Fast forward to ancient Greece in the 2nd century BC, and we have the Antikythera mechanism. This was a geared device so incredibly complex, it's literally considered an ancient analog computer. Then, jumping to the Islamic Golden Age in 1206 AD, Al-Jazari published his famous Book of Knowledge of Ingenious Mechanical Devices, which showcased these revolutionary water-powered machines and programmable mechanisms. And finally, this all just exploded in the 18th century with the Industrial Revolution in Europe, where steam power and the very first machine tools turned mechanical engineering into a formalized, world-changing profession. But that brings us to an incredible leap. I mean, how exactly did we transition from those wooden pulleys, early steam engines, and hand-drawn blueprints into a world where an engineer builds a flawless digital twin of a machine entirely inside a hard drive? Which brings us to Section 2, the modern mechanical engineer. To understand that massive transition, we first have to look at the people actually doing the work. The profile of the engineer has completely shifted from physical intuition and, tinkering in a workshop to conquering a massive mountain of rigorous academic and regulatory standards. Today, the modern engineer's gauntlet, especially in places like the United States, starts with an ABET accredited degree. That means surviving 4 years of advanced calculus, thermodynamics, fluid mechanics, and materials science. Then comes the comprehensive Fundamentals of Engineering exam. But you aren't done there. You then have to spend a minimum of 4 years working as an engineer in training, gaining heavily scrutinized real-world experience. Only then can you sit for the professional engineer exam. Once you have that PE license, you hold the legal authority to sign and seal designs that the public relies on. It's an immense responsibility, backed by serious, unforgiving mathematics. Moving on to Section 3, the Digital Engineering Trinity. So all that math and theory, it needs a digital canvas. And today, that canvas isn't some dusty drafting table covered in paper. It is entirely digital, and it's heavily reliant on 3 core software ecosystems that have basically completely replaced manual drafting and physical trial and error. The first pillar of this ecosystem is computer-aided design, or CAD. Think of this as the dreamer software. Rather than just sketching shapes, this is where concepts are visualized and mathematically defined. Engineers use CAD platforms to create highly detailed, hyper-precise 3D models. It is the absolute starting point of the modern product lifecycle, allowing designers to navigate complex geometries and assemble intricate components perfectly within a virtual space. Once those designs are finalized, the second pillar takes over, CAM, or computer-aided manufacturing. As the builder, CAM takes that pristine 3D model and translates it into the physical language of machines. It generates the precise toolpaths and outputs NC codes, like G-code, which dictate exactly how automated CNC machines, robotic arms, and 3D printers should move, how fast they should spin, and exactly where they should cut. These platforms act as this vital, incredibly complex bridge between the flawless digital model and the friction-filled reality of the factory floor. So you've designed a beautiful 3D part in CAD, and you know how to build it using CAM. But how do you know it won't just instantly break the second you put it out in the real world? Well, enter CAE, or Computer-Aided Engineering. This is the tester. CAA tools essentially simulate reality itself. They run finite element analysis and computational fluid dynamics to test structural integrity, heat transfer, and stress tolerances. They let engineers break apart virtually 1,000 times over, ensuring that the final physical product is safe, optimized, and incredibly reliable, all before a physical prototype is ever even manufactured. Now, what's really interesting about this slide is how clearly delineated the roles are within this workflow. Notice the distinct handover from the engineers designing STEP and DWG files in CAD over to the machinists using G-code in CAM to carve the metal, and finally the analysts using FEA models in CAE to simulate physical stresses. It brilliantly illustrates that while these systems are distinctly specialized, they absolutely must form a continuous, unbreakable life cycle of design, build, and test. In fact, the primary friction in modern manufacturing often lies right here, just ensuring seamless integration between these three pillars so that critical data isn't lost in translation.
Next up, Section 4, Hardware and Human Skills. Of course, running software that literally simulates the physics of reality requires an insane amount of horsepower, both in silicon and in human brainpower. On the hardware side, you can't just use a standard laptop. No way! We are talking high-performance multi-core CPUs, professional-grade GPUs for rendering complex assemblies, and upward of 32 gigabytes of RAM just to handle the massive calculations required for those CAE simulations. But here's the thing, all that hardware is basically useless without the human element. The engineers operating these machines aren't just casually picking up the software on a weekend. They carry engineering degrees, hold highly specialized software certifications, and usually need 3 to 5 years of dedicated experience to truly optimize those toolpaths and run accurate virtual stress tests. Finally, Section 5, the economics of innovation. Having highly educated professionals running beastly computers equipped with incredibly complex software means shifting a business into this digital paradigm is, well, it's not cheap. $30,000, I really want that number to sink in for a second. That is the potential high-end cost for just a single CAE simulation software license for one user. CAD licenses can easily run up to $10,000 annually, and advanced CAM setups often exceed $15,000. The upfront financial barrier to entry to implement this digital trinity is honestly staggering. And yet, that upfront software license fee is really just the tip of the iceberg. Companies have to budget heavily for hidden costs too. We're talking continuous employee training, the initial integration and deep customization of the software into a specific factory's workflow, ongoing maintenance fees, and the inevitable, painful production downtime that happens when transitioning a legacy shop floor to a brand new digital system. So, the absolutely crucial point here is, when does a company actually see a financial return on this massive digital investment? Well, it doesn't happen overnight. For small-scale production facilities, the cost savings from reduced material waste and fewer physical prototypes usually generate a return on investment in about 1 to 2 years. For medium operations, it's more like 2 to 4 years. And for massive, large-scale production, just due to the sheer complexity of the integration and training required, it can take 3 to 5 years to truly break even and start profiting from the efficiency gains. But once they do, the reduction in machining errors and the optimization of designs make the company exponentially more competitive. Which leaves us looking toward the horizon. We've gone from wooden levers to steam engines, and now to these entirely virtual testing environments. But as artificial intelligence begins to enter the CAD and CAM spaces, automatically generating toolpaths or optimizing designs for weight and strength without human input, we have to ask, what does the next evolution of mechanical engineering actually look like? Will the digital trinity become entirely autonomous? It's a thrilling mystery for sure, and one I highly encourage you to keep exploring. Thanks for joining me on this explainer, and keep questioning how the world around you is built.